This is the second part of describing distributions using numerical summaries. Whenever describing a distribution, you want to talk about its shape, which we get from graphical displays, any kind of outliers or weird stuff that doesn't fit the pattern, and then center and spread of the distribution. Those measures of center and spread are typically numerical summaries. We have median-based measurements like the median, range, and interquartile range, and then we have some measures that are based on the mean itself, variance, and standard deviation. We're going to talk today about variance and standard deviation. Before we do though, it's an interesting question. Why do we have two different types of measures? Well, the problem with using range and interquartile range to describe a distribution is that those measures only use two values from the data. Remember, range is maximum minus minimum. Interquartile range is upper quartile minus lower quartile. So we're only getting a very small snapshot of the distribution, the shape of the distribution. So instead, a more powerful approach is to use standard deviation, which takes into account how far each value is from the mean. Let's walk through a quick example. Here I have a dot plot from a small sample of individuals, and they were asked, how many pets do you have? If I took the average of this set, I see that the average is 5 pets. So let's mark that on the dot plot. Now, each observation deviates from the mean a bit. So for example, if x equals 1, then the deviation is -4. Right? We're 4 lower than the mean. Or let's take example x is 7. We're also deviating, but we're deviating less. We're deviating 2 above. So if we look at all of those deviations compared with the observations, we've got a sum of deviations. Well, the sum is 0. Well, and that's by design. The mean is sort of that middle areas point, that hinge point. And so standard deviation uses the square of deviations. So we'll add up all of the squared deviations. We'll divide by not 9, although you might think 9 because there are 9 separate deviations. We actually divide by 9 minus 1. And we'll talk about that more in just a little bit. So 52, the sum of the squared deviations, divided by 8 gives us 6.5 square pets. Well, square pets. We don't have square pets. And so the variance, which is what we just calculated, we square root the variance to give us standard deviation. So the standard deviation of this set is about 2.55, which gives us, on average, the distance the values are from their mean. So strictly defined, variance is the average of the squares of the deviations of observations from their mean. If we put it in symbols, the variance is, well, there it is. Or if we want to put it more compactly, we can use sigma notation to denote the sum of all of those squared deviations. So variance, which we call S sub x squared, is, well, it's used, but more often than not, we use standard deviation. So standard deviation is just the square root of variance. So with the example of pets, we had our squared deviations, we added them all up, we divided by 9 minus 1, and then square rooted the business. So why should we use standard deviation instead of variance? Standard deviation is good because it uses the same units of measure as the original observation. It doesn't make sense to talk about square pets. We want to talk about pets. And so 2.55 pets is our standard deviation. Also, we'll be using standard deviation a bunch when we talk about normal distributions. That's not to say that variance isn't important. We'll still use it. It'll be useful when we combine sets of observations. That'll be in upcoming chapters. So why do we use n minus 1? So Dan Teague in the North Carolina School of Science and Math. Anyway, Dan Teague is kind of a statistics guru, and he says, unfortunately, we don't have a good or easy answer to y divided by n minus 1. The answer goes beyond the scope of the course and almost always is unenlightening. Moreover, with any reasonable set of data, it makes no whit of difference if we divide by n or n minus 1. Even so, n minus 1 is the right thing to do. Now, we'll talk more about n minus 1 when we get into the chapter on sampling distributions, which is in chapter 9. So I hate to say it, but keep that under your hat. Keep thinking about that question, and we'll get it answered later on. So some properties of standard deviation that you should know. The standard deviation, which we call S sub x, measures the spread about the mean and should only be used when we're using mean as the unit of, or pardon, as the measure of center. Standard deviation is always a value greater than or equal to 0, and the only time when we'd have it, standard deviation actually equal 0 is when every observation had the same value. Lastly, since standard deviation is calculated using x bar, by the way, x bar, remember, is the mean, then standard deviation is not resistant to the effects of outliers. In fact, using squared deviations makes standard deviation even more sensitive to extreme observations. So therefore, the moral of the story is, if you have a symmetrical distribution with no major outliers, use the mean to describe the center. If your distribution is skewed, you want to use the median because it's resistant to outliers. And so the following corollary then, we'd use mean-based measurements if we have symmetrical distributions. We'd use median-based measurements if we have a skew or if we have any outliers.